So continuing on with the IMS Fest 3 for cargo and commercial ship surveyors, delighted to welcome Chris Hallum, and he's going to talk to us about ultrasound as part of your predictive maintenance program. He's also written an article actually, which we published in the Report magazine a couple of issues ago. So if you want to go and study more on the subject, then please go and read that, or indeed I'm sure Chris will give you some contact details at the end. So without further ado, Chris, over to you.
Okay, thank you very much there, Mike. And so, yep, good morning, everybody. My name's Christopher Hallum. I am just going to make sure that this works correctly. I am the UK and Ireland manager for UE Systems Europe. Basically, in a nutshell, we are a ultrasound company that produce ultrasound equipment for condition monitoring and energy savings. A little bit different to certain traditional ultrasound technologies from the NDT perspective, where we have transmissions and receivers listening for changes in ultrasonic frequency within structures. We're purely listening for ultrasonic emissions from our assets. We were founded back in the early 1970s, and we've been purely focused on R&D with regards to this type of technology, producing equipment, producing the support and the training to go along with it. We're not a service provider. We are the providers of the equipment and the means to be able to make people self-sufficient. We're a global company, headquartered out of New York in the US. But we also have offices in South America, Asia, Europe, India, and the Middle East as well. I come under the umbrella within the European Union, where our headquarters in Europe is based in the Netherlands, and we have regional representation across many other countries within Europe. We have all of our calibration workshops based in Europe as well, so any of the equipments that ever get used come back to us for servicing and calibration needs. Today, I'm going to talk to you about how we can utilize ultrasound in a predictive maintenance approach and changing the way that we might do our maintenance practices, looking at areas of where we can use it and how we use it, and a few little case studies as we go along. So the first question I always talk about, because my background myself is I'm an electrical engineer by trade, many years time served apprentice and worked on the tools for many years. The first question I like to ask people is, do you have a plan with what you want to be able to achieve? You don't need to just keep buying technologies in to help you here and there thinking that it's going to be the cure of all problems. We need to have a plan and make sure we're implementing that correctly. So we need to think about what our plan is and thinking about things like our assets first of all. And are we doing a FMICA on our assets? Are we looking at the failure modes and the effects and the criticality analysis study of those? Maybe putting our assets into a hierarchy of criticality and what we need to be looking at. Understanding which are our bad actors, you could say, or our pinch points. And then thinking about what time we're going to allow for predictive maintenance approaches. And then also things like our preventative maintenance approaches, our timed-based approach. And also looking at run to failure on certain assets, because run to failure, some people make out to be the worst thing we should be doing, but on certain assets where there might be redundancy and things like that, run to failures can be acceptable. But we also need to think about our people as well, thinking about culture, people about ways people like to do things. As human beings, we don't like change, but change can be a good thing. And having that proactive approach to wanting to change, maybe wanting to implement new things, is something to do with culture. But then along with that is also training and development of our manpower, of our engineers, of our maintenance teams, to help us improve ourselves to do things better and slightly differently. So when it comes to predictive maintenance or condition-based monitoring, there are multiple technologies out there that can do different types of things, that can look for different types of failure modes. Now, ultrasound is one of the umbrella of these technologies, where we look at things like vibration analysis, which is very commonly used for rotating assets, thermal imaging, for example, when it comes to electrical inspections. We have oil analysis, motion amplification, and online systems for remote monitoring, especially in the current climate with COVID and being able to have access to sites and things like that. Now, not one technology is going to be the savior of all our problems. So it's about looking at what technologies can do and what they can look at and how we can use them in harmony together to help us collect the right data to get the right approach. Now, we're going to look at ultrasound and where that works, the principles behind it. As human beings, we can hear in the frequency range of 20 hertz to 20,000 hertz, 20 kilohertz, from the age of about 8 years old. Once we get to the age of 8 years old, our hearing is now mature. And from the age of 8 onwards, then, we start to actually lose our hearing. And we start at the higher frequency range and we start losing those higher key tones. So most grown adults will be able to hear approximately between 20 hertz and around 16.5 kilohertz. That's the sort of frequency range that we're listening for with our ears audibly around sites. Anything below 20 hertz is known as infrasonic range, which is a very low frequency sound. And the range that we can hear is known as the sonic range. Now, with these ultrasound devices, they start at a frequency of 20 kilohertz, all the way up to 100 kilohertz our probes can tune up to. Now, that is way outside of our human hearing range. And I'm going to go into reasons why we're using those frequency ranges as we go along here. So, the main characteristics and differences between the high and low frequencies. When I refer to low frequencies, I'm going to refer to the sounds that we can hear as being low frequencies, and the high frequencies being the ultrasonic frequencies that we use. So the low frequency sounds that we can hear ourselves are very strong and powerful at their source, and they can penetrate solid objects. We can hear sounds through walls, through windows, through solid objects. And from its source, it travels in every direction. It's omnidirectional from its source. And when we talk about multiple mode conversions, that's where it can penetrate solid objects and come back into the airborne environment. Now, high frequency sound waves are shorter and weaker sound waves. If we think about a sine wave with a level of sound, a type of sound, okay, with the higher frequencies, those waves get compressed together. And these high frequency sounds are highly reflective. They bounce off solid objects. They do not penetrate a solid object. And because of this shorter, weaker wavelengths with these ultrasonic waves, the sound is more directional from its source. It only has a single mode conversion, and that is from where it's coming from. So it comes into the airborne environment, or it becomes trapped in a solid structure. It does not pass through. So if we're using an ultrasound device, we can hear the sound as we point towards it, and as we move away from it, we lose the sound again. So it helps us with pinpointing the source of the sound. And because it cannot penetrate a solid object, we can use a stethoscope to listen to the ultrasonic emissions trapped in a solid structure. Now, ultrasound is generated in two ways. The first being turbulent flow. So think about a compressed gas or compressed air line, for example, and you have a leak, it will generate turbulence. That turbulence will generate high frequency sounds. Larger leaks will generate audible sounds that we can hear, like a hissing sound, but even the smaller ones that you cannot feel, hear, or see are picked up with the ultrasound devices like it is a large leak. The second way ultrasound is generated is through friction. So think about a rotating asset like a bearing or something like that. As that rotates, it causes friction. That in turn will cause ultrasound. That will be trapped within the solid structure, and we would use a contact approach, a stethoscope, to listen to that friction within the bearing being generated. So I'm just now going to cover the applications where we can use ultrasound, because ultrasound is a very versatile technology. And with these probes, we have headphones that we listen to the ultrasonic frequencies that are modulated and heterodyned into an audible signal. So a lot of people ask me, what do I expect to hear from these assets? Well, it's exactly what you would hear audibly if you could. It's just that we're now picking it up at a higher frequency range, so we can pick it up at an earlier stage. So we can use the ultrasound device for electrical inspections, for valve testing, for checking for leakage of valves and steam traps. We can use it for our bearing inspections and to help us improve our lubrication because of the levels of friction generated. Steam trap inspection alongside valves, it's a modulating valve so we can understand the condition of our steam traps, and also for leak detection. And that can be in different types of leaks as well, from compressed gases to things like hatch testing for water tightness or for vessels for air tightness. And I'm going to go into each of these as we go along. With this technology, we have two approaches that people use this technology for. The first being energy saving. Things like compressed air systems, compressed gases are not free and they can be quite expensive. So if we can identify where our leaks are occurring, we can then use the technology to quantify them and report on them to show potential cost savings. The second side of the use of the technology is condition monitoring, is trending of our high frequency emissions from our assets, because ultrasound is our first early warning detector of a potential impending problem. When we look at things like the P to F curve, ultrasound and high frequencies are the early changes in the condition of an asset. So we can use this as our flag to say that there is a change in the condition of our asset at a very, very early stage. So the first application, one of the most commonly used for ultrasound use, is leak detection. And we're looking at four main reasons as to why we use ultrasound to track down our leaks and that can benefit our plants or our sites. First of all, being safety. Compressed air leaks, gas leaks can produce quite a big safety issue, especially if we have flammable gases present with us. Looking at the economic side of it, compressed air systems are not very cheap to run. They can be quite expensive, and on large plants with multiple leaks, we can see quite a large cost to the site. Also, looking at the environment, the more energy we're using on our compressors, for example, to keep our pressure levels up, the more horrible gases we're then eliminating into the environment. So if we can improve our energy savings, we can reduce our energy emissions to improve those things. But the last one is quality assurance. So we also use this technology for things like water tightness testing. We look at our vessels for making sure that they're sealed, because if a asset or a hatch or something is perfectly sealed, then we should hear no sound penetrating that. But if there is the slightest of air gaps, then the ultrasound will penetrate, and because it's directional, we can pinpoint its location. So a large percentage of energy wastage can be through compressed air systems. As much as 30% of a site's energy costs can be down to leaking air compressors. Repairing our leaks can reduce our compressor running hours, so again, prolonging the lifespan of our compressors. It can help us with potentially reducing the line pressure required to operate our machinery. We can also use this device and this technology in noisy environments. The noisy environments are noisy to us in the low frequency spectrum. We're not listening to those low frequency emissions. So we can use it in noisy environments because the ultrasound is also very directional. So we can point at our assets and understand what sort of emissions are coming from them. And then with the technology, we can identify these leaks and we can report on it using certain applications that you can download and use alongside this to generate reports. And an example of a report here, this is one that I did last year, just in the space of about 20 minutes in one large room in a plant. And as you can see from this, we can identify individually each of the leaks, and we can then quantify them and then show the sort of costs that we're losing per year per leak, which then is a great win to share with the site energy managers and quality people to prove that if we can repair these leaks, we can have potential savings. And then along with these leak reports, You can also generate pictures, identify it so that you can pass this on to users on site to be able to then go out and fix these leaks. So leak detection is quite an important one. Now, I only give an example here in the compressed air side of things, or compressed gases, but we can also use it for things like vacuum leaks on vacuum systems, because a leak is a leak. It generates turbulence. So in turn, it generates ultrasound. And because it's directional, we can pinpoint this. Other ways we might see this is where we may be not able to pressurize our vessels, for example. The best example I can use for this is on a ship, where I've done many hatch testing for water tightness. Now, a hatch doesn't have to be airtight to be watertight. So what we can do with this is we can use ultrasonic tone generators. We can then put that inside the hatch. We can then seal up the hatch and scan around the edges of that hatch to listen for our ultrasonic tone generator. Now, if it's a perfect seal and it's airtight, we will not hear the tone generator. But if we have the slightest of gaps, we will pick this up. Now, we have done many pieces of work in the industry with this. There are standards already in place with the likes of DNV with water tightness testing using ultrasound. Now, as a rule of thumb within these standards is that we take a reading of the ultrasonic tone generator with the hatch in its open position. We get a value, and then we are allowed a leakage rate of up to 10%. If it's below 10%, the hatch is deemed watertight. Because look at the particles and the physics behind it, we don't have to be absolutely airtight. But anything above 10% of the open hatch value tells us it's no longer watertight, for example. And again, because ultrasound is directional, we can pinpoint exactly where that's done. And we've compared this with things like chalk testing in the past, and we can be very accurate with actually where our leaks are occurring in this sort of environment and application. So very, very useful way of doing it. The next side of it is steam trap inspection. This is another potential energy savings drive, because steam, again, is an expensive commodity to run. Now, to make sure that our steam systems are running as efficiently as possible, we have in place many steam traps, removing the condensate, holding back the steam. There's many different types of traps out there that have different purposes and work in different ways. Basically, they're regulating valves. So if we have a valve that is leaking, for example, we will have turbulence within the outlet of the trap or the valve. And we can pick up that turbulence through the ultrasound using a contact approach. And as long as we understand the type of trap that we're inspecting and how it is to operate, we can listen for it opening and closing or modulating. And then when it's closed, we can determine whether it's leaking or not, just by simple listening to turbulence. So some of these slides I may have already talked about just before then. So like I say, many different types. We need to understand how they operate to understand what we're picking up. And we have two types. We have the on-off type that open and close. And then we have the continuous flow traps that are designed for high levels of condensate to release steadily the amount of condensate continuously through the system. So I'm just going to give some examples now of some sound files that you can use with the ultrasound to pick up these. And this is an example of a thermodynamic disc trap that opens and closes, and you can hear the rise and fall of the turbulence within that trap. So hopefully this will work. So from that sound recording, you can hear the opening and closing of the trap, the turbulence increasing and then decreasing. So that is what we want to see. So that tells me it is a good trap. Here's another example of a different type of trap. This is a continuous float thermostatic trap that has a ball float within the actual body that will rest on a bed of condensate. And as the condensate increases, lifts up the float and opens up the trap to allow that condensate to have a steady flow. And within this, you may hear the rattling of the metallic float inside against the body. But then we listen behind that for the low levels of turbulence.
Have I lost you, Chris?
Of turbulence.
I think,
So,
Chris, we've lost your presentation.
Oops. Yeah, I just noticed. I think we've had a bit of. We do like a bit of live feeding, don't we?
Of course, it's all part of it.
Yep. Let's exit, minimize video. I need to just share the screen. There. Hopefully, this is back now.
We're back.
We're back. Did we miss much there? I don't think we did.
I don't think so. No. We didn't catch the second bit of video I think you were trying to play.
So we were on this slide here, and we were talking about continuous float traps. Yep.
Yep, that's correct.
Okay. So a continuous float trap will allow the steady release of condensate. So what we're going to listen for here is a float within inside the body on the bed of condensate, and as that condensate builds up, it will lift the float, allowing the trap to open and remove the condensate. So we will listen here for a rattling sound maybe of the float itself on the body, and behind that a steady level of turbulence that is now present because of the releasing of the condensate. So we can hear there the rattle of the float on the body of condensate. It's bouncing against the sides of the actual chamber. But behind that, we can hear that turbulent flow as it's opening and closing and modulating nice and steadily. And that's an example of a good continuous float and thermostatic trap. Now, when traps fail, 9 times out of 10, they fail in the open position. So they are continuously blowing through the condensate, but also losing the steam. Now, one way people have inspected these in the past is by using thermal imaging. The inlet to the trap should be a higher temperature than the outlet because it's holding back the steam and releasing the condensate, which is a lower temperature. So we may get an image like this that tells us that, wow, the outlet is the same temperature as the inlet, which is an example of it maybe not working, for example. But we don't know the full condition of the trap at this point. We might see it that the inlet is higher temperature, the outlet is a lower temperature, which, according to the principles, would say that it's a good trap. But does that mean that the trap is working correctly, or does that mean that the trap is blocked, for example? Because that would still present what would look like in a thermal image to be a good trap. So using ultrasound alongside this can actually then help you with getting a better idea using multiple technologies to confirm the condition. So this is the sort of sound we would expect on a failed trap. Continuous flow, high levels of turbulence that is not modulating, not opening and closing. It's a bad trap. And this is what I find on a regular occasion in a lot of sites. So, like I was saying, having a two-technology approach can really help us with understanding the condition. Sometimes by using just one technology, we only get one part of the picture. And evidence is key with regards to this. So a little case study here now on a thermodynamic disc trap, and this was at a site looking at multiple different types of traps. But to start with, we were comparing apples for apples, the same type of traps, to see what the conditions are. So this was a recording, first of all, of a thermodynamic disc trap, and this is what we found. So as we can see from the sound recording, in the window of a 20-second period there, we could see two open modulations of the trap opening and closing. Now, a thermodynamic disc trap is, in a good working order, should modulate 2 to 10 times per minute. So we can see that if we spread this over the space of 1 minute, we would be well within the regions of a good working trap. So this is a good example of a good thermodynamic disc trap. On the same site, go into another type of these traps, and this is the sort of sound that we could hear. So over the same period of time now, we can see that this trap is opening and closing, discharging condensate, but the rate that it is now discharging and opening is a much higher rate and would be way above the 2 to 10 times per minute. So this is an indication that this steam trap is on its way out. It is showing early signs of impending failure. It's working right now, but not as efficiently as it should be. So again, early indications, early diagnosis, so that we can then plan and prepare our work that we need to do. So again, a nice early indication of an impending change. So that's the first two applications we've looked at there, more for the energy saving side and quality assurance side of things, with leak detection on vessels, on compressed systems, on valves and steam traps. So the next area is looking at condition monitoring, looking at mechanical inspections with these equipments. So there's always this big topic of discussion about reliability and improving reliability within our assets. Now, the way I see it, as maintenance staff, as engineers, we're trying to actually improve the availability of our assets. We can't improve the reliability of our assets until we start doing things like identifying potential problems, looking at the root cause of those assets and those problems, feeding that root cause analysis back to the designers, so that the designers then can change the design of an asset to help improve the reliability. Reliability is built into the asset. All we can do as engineers and maintenance staff is improve the availability, making sure that that asset is available as and when needed. So many people would have seen these charts, the DIP to F curve, looking at the original design of the asset, looking at how we install it using the correct technologies, things like laser alignment and things like that, to make sure that installation is done correctly. Because if we don't install an asset correctly, it's already going to be on its way to a failure at an earlier stage than it should be. And then we're going to use technologies to help us identify characteristics of a problem at the earliest stage. And ultrasound is, like I said earlier, one of the earliest changes in condition that we can pick up, but we can also use it before the potential failure has occurred, because we talk about friction, and then we can use that to help us with our lubrication program, because our assets will generate friction even from the day it's installed and it starts running. And as that lubrication level starts to reduce, the friction will increase. So we can use the ultrasound using things like grease caddies that we use, and listen as we lubricate to improve that friction level, to avoid over and under lubrication, and keep it running at its most optimal level for its longest duration. And if we're doing that at the early stage before there's a potential problem occurring, we have our baseline data, so we can pick up changes at an earlier stage already. So with regards to using ultrasound for mechanical inspections, we're using the contact approach. We're using a stethoscope because the friction generated in the bearing is trapped within the solid structure. So we can listen then in the structure for the shear wave that is trapped within the asset. Now, a good bearing that's adequately lubricated will present hopefully lower levels of friction and still in turn generating ultrasound. So as we get a problem with the bearing or a reduction in lubrication, we're going to see increases in our ultrasound levels. We may even see changes in the tonal quality. Now, a good bearing should be smooth and uniform in nature. And as the lubrication level starts to reduce, that smooth, uniform sound becomes louder, becomes a higher decibel value. As we then start to see microscopic damage or low levels of damage, we will start to hear that quality change and become more coarse and maybe sporadic, impacting sounds at the earlier stage. So audible quality is also very important when we're doing this. It's not just about trending the emission and the level, it's about what can we hear. So an increase in amplitude as well as a change in the audible quality can indicate an early failing bearing. It's not to say that it's going to fall over straight away because we're picking it up at the earlier stage, but it raises that flag. So a couple of examples here of some bearings and how they sound. So a good bearing should sound something like this. Smooth, uniform white noise. On the early stages of a bearing failure, so in there we can hear all of these crackling noises now sporadic, the non-uniform because it's a very early stage of physical damage within the bearing there. And then when we get to the extreme levels of it, would sound something like this. And before you say it, no, that is not a family of canaries stuck in a bearing. Those sort of sounds we can hear there is a lack of lubrication, physical damage occurring, and we pick up things like this all the time. Now, the good thing about ultrasound is that traditionally vibration analysis is used in all of our assets, picking up the levels of vibration from and changes in the condition. With the ultrasound, it uses similar principles, using spectral analysis, FFT, time waveform to pick up the levels of friction. The good thing with ultrasound is that we can use this on slow rotating assets, very slow. Single figures, large bearings, we're picking up the friction. As long as it's moving, there is friction, there is ultrasound. So we can pick it up very early. So I just want to give some case studies here on some things that I've come across in my time as we'd use this equipment for inspections. So we have here a motor driving a pump, and first time on site, never used ultrasound before on these assets. So we look at doing what's called a comparison method. You looking at like for like assets and getting a gauge for what's actually happening. So we looked at the drive end bearings of two motors that were like for like and measured on the same points. So as you can see from this image, we're listening at a frequency range of 30 kilohertz, and we can see a decibel value of 29 decibels. But we also need to understand the tonal quality, and this is what it sounded like. Smooth and uniform. Now, in my opinion, with my experience, the bearing sounded a little bit dry, and I think this sound could have been improved by applying some lubricant at the time. But we can still see a smooth, uniform pattern of sound. So that's something for us to start with. And this is good. 29 decibels at our baseline value for this one to start with. The next one we came to, like for like, same speed, load, type, and everything else. And we can see now this one, at the same point on this one, is at 61 decibels. That's quite a large increase in sound. Then we have to listen for the tonal quality. So we see an increase here of 32 decibels. Now, with baselines, for example, we set alarm levels. Now, 8 decibels above the baseline is like a lubrication level alarm. 16 decibels above the baseline, we're going to start seeing low-level damage to the bearing. When we get to 35 decibels and above the baseline, there is serious problem occurring and work needs to be looked at to rectify that as soon as possible. The next sound I'll play is from this drive end bearing for this motor. As we can hear from this sound recording, the sound is a lot coarser than the previous. It's no longer smooth and uniform. On the FFT, when we looked at this, there were harmonics identifying multiple problems with this. The next week, the site took this motor out of action to look at the repair. As they removed it, the bearing just fell to pieces. It fell out of the actual motor. It was gone, way beyond repair, and it would, if left, would have seized eventually, causing a bigger problem. So a great way to identify condition. So as you can see here, these were the two motors using FFT and time series. We can see on the FFT here, the white trace being the good one, the green trace being the bad one. The carpet level was much higher. We're getting harmonic markers to identify that there's multiple problems in here within the raceways and the cages. So we can see quite clearly from here that there's a problem that needs rectifying. Another case study here being a reduction gearbox. So again, rotating parts should be smooth and uniform in nature. And again, we can compare like for like. So on here, we're going to we've listened on the body of the gearbox, and we're just listening for what's going on inside that body of that gearbox. Smooth and uniform in nature, that's just what we want to hear. The next one, like for like, very similar, measured on the body, and this one presented a different sound. So from this one, we can hear the repetitive impacting sounds that could relate to damaged teeth within the gearbox itself. We're hearing a high squeaking sound, which also tells us there could be a problem with the level of lubrication. Looking maybe at the oil levels in here. But again, a clear indication of something not right with this gearbox. So we can see it at a nice early stage. So I was saying earlier that one of the key areas for using ultrasound is looking at our slow rotating assets, because they generate a low level of ultrasound, but the tonal quality can be very clear and very obvious when we're looking for any potential problems. The slow speed produces lower levels of ultrasonic emission because of the lower levels of friction, but we can still pick up these sounds. It allows our inspectors to obviously identify a problem, giving the inspector the ability to easily assess the condition. Now, these are extreme slow speed bearings, a good example first of all. You could barely hear anything there at all. And that's right, because a extremely slow speed bearing that generates very little ultrasound will generate very low levels. But as soon as it starts to show problems, we will hear it very quickly. So a good slow speed bearing smooth, uniform white noise. That's just what we want to hear. One that's not so good we start to hear the coarse sound, we hear repetitive impacting sounds, crackling noises that indicate a condition of the bearing is deteriorating. So from the first two sounds to the last sound just there, you can hear a clear difference that indicates a problem. Now, here is a case study on possibly one of my most favorite finds I've ever had. I was just visiting a site where they manufacture, it's an OSB plant where they manufacture chipboard. So part of the process is that the logs come into the site, they get debarked, chipped down, and then these chips have to go through a large cylindrical oven dryer to dry the chips out, to come out the other side to be made into chipboard. Now these large circular dryers are rotated on motors at a very slow speed. The asset we were looking at the time was only installed about 6 months prior to us being there. Now, they all had the same type of motors, running the same speed and load, so we can do a very simple comparison method just to inspect the condition. So straight away, we use the ultrasound on the motors to listen to the condition. So there were 8 points for us to monitor. And because the emission was so low, the decibel reading was 0 dBs.
Can you hear mine?
Hello? Right. So 0 decibels, very low level of ultrasound, but we could still hear the tonal quality. And 7 of the bearings sounded just like this. Very smooth, very uniform. We could perform a sound recording and use that as our baseline. One of the bearings, though, as we came to it, was registering 2 decibels of sound. Now, 2 decibels doesn't sound like much in comparison to 0, but that's a 200% increase compared to the 7 others on this asset. And on there was a repetitive sound that we could hear. And this is what it sounded like. So through the laptop and through the computers right now, that sound is being amplified. But in the headset, it was a very low level knocking sound. Now, the other technologies they had on site were not picking anything up. They were not convinced that there was a problem because this asset was only 6 months old. So let's use other technologies to help us. So a grease sample was taken and metal particles were discovered within the grease. So we know that there's a physical problem. We can see from the time waveform the repetitive impacting sounds that tells us there is a problem present. So on this evidence, action was then taken. They took it apart and sent me these pictures. Large cylindrical bearings, we can see that the outer race had cracked quite severely, the cage had been damaged, and one of the rolling elements had even moved 90 degrees. And we can see that from our time waveform as we look at the sound pattern from this. So a great way of finding a problem. It turned out that it was a damage caused on installation here. But again, very early detection, big problem, avoided unscheduled outages. That's the important thing, is being able to identify something so that you can plan and schedule. So access to critical assets can also be a bit tricky at times. These days, with more safety barriers and guarding putting in place, it means that restrictions can be there for us to monitor our assets. But it doesn't mean that we can't monitor our assets. We could use online sensors, remote sensors, where we can plug in probes to then be able to take readings without breaking these barriers, improving our data collection time even. Also, things like online monitoring systems, so that we can maybe monitor our critical assets without having to visit those areas. An example here being the forecast system that can then continuously monitor over a network the condition of our assets with simple friction levels, ultrasonic emissions, and sound recording ability. So we can then look at it from our computer without having to go to our site or even to the assets itself, trending the decibel values. And the newest innovation in online monitoring and remote monitoring with ultrasound is looking at using remote condition monitoring of the friction, and at the same time having the ability to remotely lubricate without having to go to site from anywhere, from even your phone or even your computer, from anywhere in the world, using an on-track system where you can then monitor your assets using sensors, listening to the friction level, setting alarm levels on a dashboard that you can access from any device that can use Internet Explorer or Chrome or anything like that, and then looking for those alarm levels, and then on an alarm level, being able to action single point lubricators to actually lubricate that grease on condition, and at the same time while trending the friction level without having to visit the assets. So we now talk about lubrication, and we're moving into that area. So we're talking about right now, up until now, talking about mechanical inspections, understanding the condition, but condition-based lubrication can be something really advantageous with using this technology. So it's a simple way of doing things by listening to that friction level, understanding what the bearing needs and what it wants. So when a bearing calls for obviously lubrication, we're seeing an increase in friction. And as we apply grease, that friction level is going to reduce in turn. And because that friction level is reducing, we can then continue applying grease until our friction level no longer goes any lower. Once the bearing friction doesn't go any lower, we stop applying the grease, because that is the bearing telling us that it does not need any more grease. So sometimes people will use a time-based approach to this. After so many running hours, it'll be so many shots every so many months. But is that the right amount? And this is where, using ultrasound, we can listen for the right amount. So a good bearing being lubricated will sound, well, a good bearing will sound smooth and uniform. Now, this is a sound recording of a bearing being lubricated. So as we hear there, the friction level starts to decrease and decrease as we apply the grease, which is perfect, because then we know once it doesn't go any lower, we stop applying the grease because the bearing now has enough lubrication. So we can see from this trace on the screen in front of us on the time waveform, as the grease is applied, we see the friction level reduce, and that's where we stop. If we carry on applying the grease, we're going to over lubricate, which will cause more pressure within the bearing and more friction, and we can see the sound start to increase. So if the sound increases as you apply grease, then we stop, because that bearing has enough grease. So we lubricate slowly, and we lubricate until the decibel value returns to its baseline or doesn't go any lower. If the value increases, we stop lubricating, as over lubrication is imminent. So with regards to bearing inspection, ultrasound can be used as a first technology of implementing a PDM at an early stage. It's a very simple technology to learn to use, because it's using our human senses. And it can be used in conjunction alongside things like vibration analysis, oil analysis, to improve the data that we're getting. And ultrasound's key area is lubrication and slow speed bearings. We're really useful for those areas. Another way of using ultrasound is for electrical inspection. So if we have any sort of discharge from an electrical asset, that discharge is going to cause turbulence in the surrounding air, in its environment, and that turbulence produces the ultrasound. It's, again, using it as an efficient method for detecting electrical faults in early stages. It's non-intrusive. We don't have to have assets open. We don't have to be in too close to the assets. We can do it from a safe distance. So what can we detect with ultrasound when it comes to electrical inspection? So things like corona discharge, tracking, arcing, partial discharge, some people might refer to it as that, and also mechanical looseness. So advantages of using ultrasound, like I was saying earlier, is that it's non-intrusive. We don't have to have eyes on the assets to pick up the emissions. We can inspect from safe distances. We can inspect on closed systems. We don't have to have them open. We can use a contact approach to listen to what's going on inside our assemblies. And we can use it in combination with thermal imaging. One sees the problem, the other hears the problem. So I always like to champion a two technology approach because having key data is important, hearing and seeing the problem. So a couple of case studies here, 400-volt buzz bar on a distribution panel. Cabinet is closed. We're going to use a contact approach without having to present any other risks. No moving parts inside, so there should be relatively no sound, if any at all. And this is what was picked up. So from that, we can quite clearly hear discharging occurring, partial discharge within the asset, inside that cabinet that's presenting a problem. That inspector has not presented themselves any further risks because they have got the cabinet still closed, but now they've identified a problem so that now they can say, right, we need to access this, but we need to power it down first because there is a problem inside. Great way of inspecting. Another one here is a cabling issue. So this was a high-rise building. A service provider shared this with me. They were inspecting some 11 kV transformers. And what they do first of all is they go into the room, they inspect with ultrasound, listening for anything abnormal. If there's nothing abnormal, they'll then carry out their thermal imaging inspections. But in this instance, they picked up a sound. So ultrasound being directional, they could then follow the sound where it was coming from, and it was coming from some 400-volt cables. They pinpointed where the source of the sound was coming from, pulled out the thermal camera, and they could see a slight rise in temperature between some cabling. On closer inspection, they could see marks of heat buildup and damage occurring. From the sound file, they were analyzing tracking was occurring. So they turned out the lights and they pulled out their camera to do a video recording. If you pay attention to the middle of the screen, you'll see the evidence of tracking occurring. So this was a very early level problem with tracking. The cables were incorrectly mounted too close to each other. There was a buildup of VMF, the heat buildup, breaking down of the insulation, causing tracking to occur. Eventually, this could have caused a very serious problem. But using ultrasound and then confirming the point with thermal, they could identify the problem. Enough data to justify their need to do rectification work. Great way of doing things. So always be safe when you're working with electrical inspections. It's always important to understand what you're looking at and how to treat things. Ultrasound does not replace thermal imaging, it complements it. It can be used as an added safety barrier because it's non-intrusive. We don't have to have eyes on. So in conclusion to this little presentation, ultrasound can be seen as a very versatile technology. There's multiple uses for this in multiple areas. It's simple to implement because it's using simple understandings of the sounds we're picking up. It's very easy to get used to, get our operators on and get trained on. We should be looking for energy savings, improving our quality and what we're doing. But also looking up, focusing on our functional failures we experience to deploy the right technology to identify them. Most PDM technologies will complement each other as well, having them side by side, but also train and educate the workforce on how to use these things. For a PDM program to be successful, culture change is also key from all levels throughout the chain, making sure you have buy-in to make sure that you get the best from your results here. So I'd like to thank you all for your time today. My details are on the screen as you see. We have a website that has lots of good information and tutorials and information there that you can use. And we are always happy to help people out whenever needed. So I'd like to thank you for your time.
Chris, thank you very much indeed. Gosh, I don't think I'd appreciated just how versatile ultrasound is. So, you know, it's always nice to bring into a day like this something a little bit different from marine surveyors, and I hope that's what we managed to achieve with this presentation. I have a question from Greg, who has asked, can ultrasound sensors be attached to a submerged housing, such as a Z drive, to listen for bearing condition?
So the sensors themselves, we have got sensors that have been used in submersible areas. It depends obviously what sort of depth we're looking at and things like that, but there are sensors out there that we do have, yes.
So the answer is yes, Greg. Fantastic. Any other questions before we let Chris go?
So I think one of the key areas that for the sort of sector we're looking at the moment is we do a lot of work with hatch testing, water tightness testing and things like that. And we have worked with the likes of DNV to create these sort of standards approach, and all of our probes are registered within the DNV as acceptable tools for these inspections. So those are areas that can be quite useful and help improve the speed at which you do the inspections of the hatches.
Okay. Fantastic. Chris, thank you very much indeed. Appreciate you giving up your time, and thank you for sharing your knowledge.
Oh, you're welcome.
And, we'll catch up with you again soon, I hope.
No problem, absolutely.
Many thanks.
Thank you very much, guys. Thank you.